Carbon nanohorns. They are one-dimensional carbon nanostructures with a conical shape and exceptional properties compared to other carbon nanostructures. Hello everyone, it's Shiv, and today I'm going to present our project on the material carbon nanohorn. The base element of carbon nanohorns, as the name suggests, is carbon. Its atomic properties are as follows. The atomic number is 6, the atomic mass is 12.01 AMU, the covalent radius is around 77 picometers, the electron affinity is about 1.26 electron volt, the electronegativity is about 2.55 on the Pauling scale, and the first ionization energy is approximately 11.26 electron volt. Optical, mechanical, and electrical properties. Carbon nanohorns exhibit unique optical properties that arise from the curved graphene-like structure. Mechanically, they have high strength and stability due to a robust hexagonal lattice similar to graphene. These nanohorns also demonstrate excellent resistance to harsh electrochemical environments, making them highly corrosion resistant. Electrically, they have enhanced conductivity, especially when doped with elements like nitrogen or boron, which, combined with their large electrochemical surface area, makes them ideal for applications in batteries, fuel cells, and supercapacitors. Moreover, their ability to perform electromagnetic shielding adds to their attractiveness for various electronic applications. Allotrope family and assembly behavior. Carbon nanohorns belong to the allotrope family, along with graphene, fullerenes, and carbon nanotubes. They are generally preferred for high purity applications because carbon nanotubes require metal catalyst during synthesis, while carbon nanohorns do not. Due to weak van der Waals interaction, carbon nanohorns self-assemble into spherical flower-like clusters. This self-assembly results in a very high surface area of around 1000 meters square per gram and a highly porous nature, making them ideal for adsorption-based applications and catalysis. Their hexagonal lattice structure, similar to that of graphene, further contributes to their unique packing density, charge transport, and mechanical stability. They also interact well with metal nanomaterials and can perform solid dispersion in polymers, influencing phase behavior, miscibility, and conductivity, and even exhibit isomorphous behavior when mixed with other nanocarbons, allowing for tailor-made properties. Thermal stability. Carbon nanohorns are quite thermally stable, maintaining their structure up to around 2000 degrees Celsius in vacuum, making them suitable for high temperature applications. Synthesis methods. There are two common bottom-up synthesis methods for carbon nanohorns. First one, the arc discharge method. In this approach, a pulsed arc discharge is generated between pure carbon electrodes or rods in an atmosphere of inert gases, such as helium or argon. At atmospheric pressure, the carbon rods are preheated up to around 1000 degrees Celsius and continuously rotated so that a fresh surface is exposed to the arc. The high-energy arc vaporizes carbon, which then recondenses to form the nanohorn structures. Since the process builds the structure atom by atom from the vapor phase, it is classified as a bottom-up approach. The second one, the CO2 laser ablation method. This method employs a high-power CO2 laser whose wavelength is around 10.6 micrometer to ablate a rotating graphite rod in a controlled inert atmosphere at room temperature. The ablated carbon vapor cools rapidly and nucleates to form the nanohorn structure. Like the arc discharge method, this is also a bottom approach since the structures are assembled from the carbon atoms in the vapor phase. Phase diagram of carbon. The phase diagram of carbon is key to understanding its allotropes. At standard atmospheric pressure and room temperature, graphite is the thermodynamically stable form of carbon. Under high pressure, above 1 to 2 gigapascal, and moderate temperatures, diamond becomes a stable phase. Although at ambient conditions, diamond is metastable due to high activation energy barrier that prevents its conversion to graphite. At very high temperatures, around 3900 Kelvin at atmospheric pressure, carbon sublimes directly from solid to gas. The excellent thermal stability of carbon nanohorns up to 2000 degrees Celsius in vacuum is a reflection of these phase properties, making them ideal for applications under extreme conditions. Manufacturing. For manufacturing of carbon nanohorns, initially raw graphite is pre-treated or prepared to be fed into a high-energy reactor, which means either CO2 ablation method is carried out or the arc discharge method, as explained before. The resultant soot particle is collected and purified, and their aggregation is controlled. Then they are characterized according to their aggregation and quality, and finally packed as the final product. Scanning electron microscope and tunneling electron microscope observations. From the SEM and TEM observations, we can see the aggregated morphology where we see how the nanohorns self-assemble into spherical dahlia-like clusters which contributes to their high surface area and porosity. Each nanohorn exhibits a conical shape with a distinct tip formed by non-hexagonal rings that is characteristic of their formation. HRTEM reveals clear lattice fringes confirming their high degree of graphitization and structural order. The images suggest that as synthesized, the nanohorns are relatively free of metal contaminants and have minimal defects, beneficial for various applications such as catalysis, gas storage, and drug delivery. The role of material science. Due to the knowledge we gained from this course, we are able to understand atomic structure and chemical bonding. It provides us deep insight into why carbon atoms bond in specific geometries and form unique nanostructures. It helps us in explaining the intrinsic properties such as atomic number, mass, radius, ionization energy, etc. of carbon that governs the behavior of the nanohorns. Phase diagrams and thermodynamics introduces us phase diagrams and thermodynamic principles to predict the stability of different carbon allotropes like graphite, diamond, etc. which are related to nanohorn formation. It guides us in understanding how temperature and pressure affect synthesis of stability. Microstructure and defect. It covers the principles behind crystal lattice structures and defects, which is essential for understanding the hexagonal lattice and conical geometry found in carbon nanohorns. Explains how nanoscale features and self-assembly influence overall material performance. Synthesis and processing techniques. It familiarizes us with the bottom-up synthesis method. It also emphasizes the impact of process parameters on nanostructure formation. Structure property relationships. Teaches how variations in atomic bonding and structural arrangements affect optical, mechanical, and electrical properties. It enables us in predicting the high surface area, thermal stability, and electrical conductivity observed in carbon nanohorns. Characterization method. It provides us a basis for understanding techniques like electron microscopy, X-ray diffraction, and spectroscopy, which are key for analyzing structural and electronic properties of nanohorns. That was the world of carbon nanohorns. Thank you for taking your time and listening to our project. Thank you.